Okay, so now we're ready to talk about the dot product, which is one way to multiply two vectors. So we have two vectors, u and v, given in their component form. Right? So the definition of the dot product, we're going to denote it by taking u dot v, so just a little dot between the vectors, and it's defined to be the sum of the products of the individual components. So u1 times v1 plus u2 times v2 plus u3 times v3. Okay, so the first thing to note about this is that it's not a vector, right? You're just taking these numbers, the components are numbers, you're multiplying two numbers and getting a number, and then you're adding another number, then you're adding another number, right? So what you get is a number, a scalar, right? So this is a scalar, right? So please do not write it as a vector, right? There is no I, j, and k here, right? In fact, you could come up with a vector where this is you can think of this as a product of vectors, but it turns out to be completely useless. It doesn't really have any significance or any relevance that I'm aware of. I mean, it's possible that, there is such a thing, but I've really never come across it. So yeah, this is not a vector. This is a scalar. So the dot product is also sometimes just called the scalar product. It's the product of two vectors, but then you don't get a vector, you get a scalar, right? More generally, you can also call this an inner product, but that's a more general term which we're not going to really use here. That comes from linear algebra, for example. All right, so yeah, so another thing to note is that if you have, these are vectors in space. If you have two vectors that are just in the plane, say u1, u2 for u, and v is just v1, v2, you can still define the dot product. You just leave off the last term here, right? So it's u1, v1 plus u2, v2, right? And of course you can define this for vectors with 4 components or five components, but we're not going to see those, so these two are usually good enough, right? So maybe I'll do one very quick example, just to show you how easy this is. So let's suppose the vector u has components 7, -2, and 5, and the vector v has components 2, 3, and 4. Okay, so what's u dot v? Well, right, u1 times v1 is just 7 times 2, plus u2 times v2 would be -2 times 3, plus u3 times v3 is 5 times 4. So what do we get? 14 minus 6 plus 20. So 14 minus 6 is 8. 8 plus 20 is 28. As promised, you get a number, right? So the dot product of two vectors is just a scalar, a number, right? Okay, good. Yes, a lot of people love to put I, j's, and k's here and to make it a vector, but that's not the dot product. In fact, that's not any product that I'm aware of. It's kind of a useless thing to do, right? We will, in the next section, talk about another way to multiply two vectors where you do get a vector, but this is not that, right? So that'll be the cross product, but this is the dot product, and it's a scalar. Okay, so that's how it works. Let's get to some properties of the dot product. Okay, so it's theorem 11.4. We have vectors u, v, and w in space, and c is a scalar. Actually, all of this applies even if the vectors are just restricted to a plane, I believe. But, you know, most of the time we're going to talk about vectors in space, right? And c is just a number. Okay. So first thing to note is that if I take the vector u dot v is the same as v dot u, that the scalar product, the dot product is commutative. So you can change the order and you get the same thing. And it's very easy to prove that. All you have to do is note that in the definition here, each term can be reversed, right? The numbers u1 times v1 is the same as v1 times u1, right? So yeah, so the proof goes like this, and I know I probably shouldn't bother proving it, but it's really easy. So u dot v, right, by definition is u1 v1 plus u2 v2 plus u3 v3, but u1 times v1 is the same as v1 times u1, and u2 times v2 is the same as v2 times u2. Same thing with the 3's, right? That's supposed to be a 3. And, well, by definition, that's just v dot u. So there you go, right? Very easy to show that one. But I'm probably not going to show the rest, right? The second property just says that if I distribute, say, u, and I take the dot product of a sum, let's say v plus w, right? And we talked about adding two vectors in the last video, so that should be clear. As you could probably guess what happens here. You just get u dot v plus u dot w. So the dot product distributes over sums, and of course you can change this to a minus, so it's the sum or difference, or just think of w as its opposite, right? So again, that's also not hard to show. You just look at all the components and you compare them. For number 3, it's a little different with when you're multiplying a scalar c times the dot product of u and v. So remember, the dot product is a number, so you're just multiplying two numbers, c times this other number. But it's associative, right? So in other words, you can take c times u first, and then take that vector dot v. Right? Or you can take the vector u and take the dot product with c times v. Right? So all of these are equivalent. Yeah, I should say c is a scalar. In this case, it has to be a real number. For those of you who've had linear algebra know that in general, when you switch from the c being u to v here, you might get the complex conjugate. But since these are real numbers, that's not an issue. So yeah, so this will always be true for us. But if you're allowing c to be a complex number, then you have to be a little more careful. This might not be true. And the fourth thing, hopefully pretty obvious, if you take the 0 vector dot v, you just get 0 as a number, right? The 0 scalar, right? And in this case, it doesn't matter, right? Well, we know the order doesn't matter, right? So this is also v dot 0. And again, that's just because the 0 vector has all three components being 0, right? So 0 times v1 plus 0 times v2 plus 0 times v3, of course, is just 0. And one more property here. If you take a vector v and you take the dot product with itself, right, then you also get the magnitude of the vector squared. And in fact, let's just write this out, right? What is v dot v? Well, it's v1 times v1 plus v2 times v2 plus v3 times v3, which of course is just v1 squared plus v2 squared plus v3 squared, right? And if you remember, the magnitude, I'm trying to get a different color here, the magnitude of a vector v is just the square root of the sum of the squares of the three components. So when you square that, you get rid of the square root, right? And you just get v1 squared plus v2 squared plus v3 squared, which is exactly the same as the dot product with the vector in itself. Okay, so yeah, that just shows that this is the same as the magnitude of v squared. Or just take v as a scalar squared. It's the magnitude of v. Okay. So the next thing we'll do is sort of the geometric definition. There's another way to define the dot product. And that's going to be the following. U dot v is just going to be the magnitude of u times the magnitude of v times the cosine of theta. Now, what's theta? Well, let's draw the two vectors here. Here's the vector u, and here's another vector v. Theta is just the angle between the two vectors. Let's try to draw a better theta there. So the theta is just the angle between the two arrows that the vectors represent, are represented by the vectors, right? Okay, so again, this gives you the same results, and again, it's probably not obvious here why this should be the same as doing this. Oops, that's supposed to be a v, and that's supposed to be a u, so there we go. Right, so that's the definition we had earlier, right? And to show these two are the same is, again, not an easy thing to do. But I think I can make it reasonable. So let's take an easy example of this. So here's the x and y plane. And so our vectors, we're just going to take vectors on the plane here. So let's suppose that u is just the vector u1i plus u2j. So two components. There's no z component, right? And let's suppose v is just v1i plus, and let's make it easy. Let's make it 0j, right? In other words, just the vector v1, 0. And u is, well, u could have two components, u1 and u2. Right, so let's draw those two vectors, right? So this could be vector u, but then vector v has a 0y component, so it just might be this vector here. Right, so pointing along the x-axis. Right. And then theta would be, well, this angle here. Okay, so let's take the dot product of those. U dot v is just going to be u1 v1 plus u2 v2. Remember, there's no third components here because they're in the plane. But remember, v2 is 0. So this is really just u1 times v1. Right? So what's u1? Well, u1 is this number here, right? It's just the x component of u, right? So u2 would be up here somewhere. Right? And notice that if I take u1 times v1, remember v1 is just that number there. If v1 happens to be 1, right? So in other words, if v is the vector I, right? So 1, 0, then u dot I is just u1, which is this component here, right? So trying to draw a right triangle if I can. It's a little better. So this is just trigonometry, right? If this is the vector u here, this is the magnitude of u. And then this, of course, is the adjacent side. So, right, so that's just cosine. So it's the magnitude of u times the cosine of theta. Right? So that's all this u1 is. It's the same thing as u, meaning the magnitude of u, times the cosine of theta. So if v is not 1, then you have to multiply by it, right? So then you get u1 times v1, which is u times v times the cosine of theta. Right? So is that clear, right? Because if I take the magnitude of v, it's just v1. Right? That's the length of the vector v. And if I take the, well, yeah, so the magnitude of u, of course, is the square root of u1 squared plus u2 squared. But yeah, so when you're taking the dot product, you're just getting the component, right? So at least in this form, this should be the dot product of u and v. Right. And if you just rotate these, you can get the more general rule up here. But it's certainly true in this specific case. So at least I hope that that's reasonable, right? That u1 is just u times cosine of theta, and v1 is just, well, v itself, the magnitude of v itself. So that gives you this formula for this very specific case. But if you want to generalize it, then you just have to worry about the third components and so forth. Okay, so that's another way to think of the dot product, a more geometric version of that. But what it allows us to do then, right, if you're wondering, well, how can I determine what this angle is, the angle between the two vectors, right? So you can do that just by dividing by the product of the magnitudes, right? So let me write this over again. U dot v is the magnitude of u times the magnitude of v times the cosine of the angle between them. So if you want to solve for theta, just divide both sides by the product of the magnitudes here, right? I hate to write it over again, but here it is. There we go, right? So the cosine of the angle between two vectors is the dot product divided by the product of the two magnitudes. Right? So we can think of this as a formula for theta. Okay. Again, maybe just an easy example. Yeah. So suppose u is the vector 2, 1, negative 1, and v is the vector 3, negative 2, 4. Okay. Find the angle between u and v. So I'm not even going to try to draw these vectors because they're in space. If these were vectors in 2 dimensions, right, if they only had 2 components each, then that would be a little bit easier. But imagine you have some vector u in space and some other vector v in space. How are we going to find this angle? Sorry, it should be a v here, right? Yeah, so we're going to use this formula. And so to do that, what do we need? Well, we need the dot product. We need u dot v. And since we have their components, that should be easy enough, right? 2 times 3 is 6. 1 times negative 2 is negative 2. And negative 1 times 4 is, well, negative 4. Oh, so you get 6 minus 2 is 4. 4 minus 4 is 0. Okay. Well, that's what happens when you make this up. That wasn't supposed to work out that way. But okay, let's just finish the example, right? So what else do we need? We need the denominators are the magnitudes. So the magnitude of u, although it hardly matters here because the numerator is 0, and the denominator is clearly not 0. But just to complete the result here, the magnitude of u is 2 squared plus 1 squared plus negative 1 squared, 4, 5. So that's the square root of 6. And the magnitude of v is going to be the square root of 3 squared plus negative 2 squared plus 4 squared, which I believe is 29. So square root of 29. So the formula is the cosine of theta is the dot product divided by the product of the magnitudes. And I'm just going to write u and v here for their magnitudes. It's getting a little bit burdensome to have to write these vertical bars here. So the numerator is 0, the denominator is square root of 26, square root of 6 times square root of 29. Whatever number that is, you just get 0. Okay. So that's not the answer, of course. We're looking for the angle. So what angle has a cosine of 0? Well, what's the arc cosine of 0? Yeah, pi over 2, right? 90 degrees. So yeah, I didn't specify radians or degrees, so I would accept either. Yeah, so it turns out these vectors, when you draw them, they might look something like this. So if this is vector u, vector v will be at, well, I got it backwards, right? Because v is the longer vector. So this might be v here, and then this might be u. So the angle between them is indeed 90 degrees. It's a right angle. Okay. So maybe not the best example because, yeah, the angles don't have to be 90 degrees. That's just a coincidence. But it does give us the following definition. So if the dot product of u and v is equal to 0, then we say that u and v, the two vectors, are orthogonal. Okay? And what that means is when you draw the arrows, like I did up here, see that? The two arrows are perpendicular. Okay? And so you might ask, why don't we just say the two vectors are perpendicular? Well, so perpendicular usually refers to lines or arrows in this case. So we can say the arrows are perpendicular. The geometric representation of the arrows, right, are perpendicular. But the vectors themselves are orthogonal. On the other hand, if you just say, look, the two vectors are perpendicular, I'll know what you mean, but we like to use the word orthogonal when describing two vectors when their dot product is 0. Right? Because remember, some vectors cannot be represented by arrows, right? Say they have infinitely many dimensions or something. In that case, if the dot product is 0, they're orthogonal, but it's very hard to visualize them as being perpendicular. Okay, so yeah, so again, this you have the alternative version of the dot product as well as the formula for the cosine of the angle between two vectors. And so maybe I'll do one more quick example where you don't get 0 for the cosine of the angle, just to show you that in general that's not going to happen. So let's suppose u, and we'll just do this in 2 dimensions, right? So suppose u is the vector 3, 7, and the vector v is 5, 2. Right. So now find the angle between them. Right. So, so we're going to use the same formula, of course, u dot v divided by u times v. So u dot v, of course, the dot product, is 3 times 5 plus 7 times 2. So 15 plus 14 is 29. And then the magnitude of u, or just u, is going to be the square root of 9 plus 49. So that's going to be the square root of 58. And then the magnitude of v, or just v, is going to be the square root of 25 plus 4. So we saw that earlier, square root of 29. So, right, so in the formula, the numerator is 29. The denominator is the square root of, 58 times the square root of 29. Yeah, and this works out quite well because you can cancel one of the square roots and you just get square root of 29 over square root of 58, which I believe is the square root of 1/2. Well, that was another coincidence, right? So 1 over the square root of 2 is the square root of 2 over 2. Right. So now, to find the angle itself, we just take the inverse cosine of square root of 2 over 2. And I hope you know that by heart, right? That's your pi over 4, or 45 degrees. In general, of course, it's not going to work out to, you know, an exact angle like this. Very often you'll get angles like, 23.9146 degrees, because you typically have these square roots, and then to get the approximate angle, you just have to take the inverse cosine using your calculators. Yeah, so I'm coming up with very nice examples here, but again, keep in mind that the examples are going to usually end up with not so nice numbers. And, if you ever want to represent the angle exactly, you can just do it as the inverse cosine of some number, right? So let's say 3 over the square root of 24, just making sure. So what would that angle be approximately? So run to your calculator. And I get about 52.23, well, we'll say 2 decimal places. We'll say 52.24 degrees. Right. Oh, and notice that the angle does not have to be acute, right? You can have an angle between two vectors. I should do this. So let's say one vector points this way, and another vector points this way. Now the angle between them will certainly be bigger than 90 degrees. And remember what happens, right, when the cosine of the angle is negative. Right, here the cosine will be less than 0. And when that happens, your angle will be between 90 and 180 degrees. Right. Oh, and of course the dot product could be negative. It's just a sum of these components, and if some of the components are negative, you can certainly arrange for the dot product to be a negative number as well. So the dot product could be positive or negative, or 0. And if the dot product is 0, as was the case in this example, that's a special case where we say the vectors are orthogonal. Okay. Moving on to another definition involving the dot product. Okay, so we have a vector u in space, right? So it has 3 components, and I'm going to write it both ways. And let's suppose the vector is represented by this arrow here, right, in the usual xyz plane. Again, very hard to visualize, so let's do the following. Let's see if we drop this down, and then it hits the xy plane, let's say right here. So now we can think of this as the shadow of that vector on the xy plane. Right. So in other words, if the vector u has components u1, u2, and u3, this vector down here, which I can't call u anymore because it is a different vector, I guess I'll call it w. This vector will have components u1 and u2, but then the z component will be 0, right? Because it lies in the xy plane, it doesn't have a vertical component, right? Okay, so yeah, so that helps. But now the question is, what are the angles between the original vector u and, say, the x-axis, right? So the angle between the vector u and the x-axis is just some angle. So I'm going to give it a name. I'm going to use the Greek letter alpha for that angle. And then we can talk about the angle between u and the y-axis. So that's this angle here. Of course, I'll use the Greek letter beta. And finally, we want the angle between the vector u and the z-axis. And for now, we're going to use gamma, although we're going to switch to a different Greek letter later. But for now, alpha, beta, gamma. Okay? So how do we determine those three angles? Well, we know how to determine the angle between any two vectors. So let me just remind you of that formula here. Right? But these aren't, right, the x-axis is not a vector. The x-axis is not a vector. However, we can make a vector in the x direction. Right? So any vector in the x direction only has the first component, right? The the u1. Or we should use a different vector, say v1, right? Well, and let's just make it length 1, right? So let's use the vector I here. And notice I'm going to put a hat over it. I guess I'm switching to hats now because I just find them a little more convenient. So this is the unit vector I. Remember, the unit vector I just has components 1, 0, 0. Okay. So let's take the dot product of u and I. So that's going to be the following, right? The vector u, as we defined above, u1, u2, u3. And if we take the dot product with I, which is just 1, 0, 0, well, no surprise, we just get u1. Okay? On the other hand, remember, there's another way to compute the dot product. We just have to compute the magnitude of u times the magnitude of the vector I times the cosine of the angle between them. Well, the angle between I and u, we're not going to use theta anymore. We're going to use alpha, because that's how we defined alpha here, right? Okay. So first of all, what's the magnitude of I? Well, it's a unit vector, so by definition, it should have length 1. So this is just going to be the magnitude of u times 1 times the cosine of alpha. Right? But that has to be the same as u1. Right? Or maybe I'll write it on the right here. Oh, sorry. Yep, so this is the same as u1. And so if you want to find alpha, just divide by the magnitude of u, right? So the cosine of alpha is going to be u1 divided by the magnitude of u. Or if you want to write them all out in terms of their components, this is u1 divided by the square root of u1 squared plus u2 squared plus u3 squared. And now, if you want alpha itself, then just take the inverse cosine, or the arc cosine of this quantity here. Okay, so these are sometimes called the direction angles. So they're the angles that the vector makes with each of the coordinate axes, in this case the x-axis, right? So, or if you just want them in terms of the cosine of the angle, these are sometimes just called the direction cosines. And once you have the direction cosine, then you can find the direction angle just by taking the inverse function, the inverse cosine, right? So that answers the question, how do you find the angle between the vector u and the x-axis? That's the angle alpha here. So how do you find the angle between u and the y-axis? How do you find beta? Well, you can go through this whole argument again, but I hope it's clear at this point that the cosine of beta will just be the second component divided by the magnitude of u. Right? In other words, just u2 divided by the square root of u1 squared plus u2 squared plus u3 squared. And likewise, the cosine of gamma will just be the third component of u, again, divided by its magnitude. Squared, right? So these are the direction cosines for the three angles that the vector makes with each of the three coordinate axes here. The x-axis for alpha, the y-axis gives you beta, and then the z-axis gives you gamma. Okay. And we get the following relationship between the three angles here. So if we take cosine squared of alpha plus cosine squared of beta plus cosine squared of gamma, well, what do we get, right? We get u1 squared divided by, oh, I hate to write it all out, but u1 squared plus u2 squared plus u3 squared. Actually, let's just write it as the magnitude of u. So we get u1 squared divided by the magnitude of u squared, right? Plus u2 squared divided by u squared plus u3 squared divided by u squared. And because they all have the same denominator, you just get in the numerator u1 squared plus u2 squared plus u3 squared, which is none other than u squared. So u squared divided by u squared is 1. So, yep, if you square all these direction cosines, right, cosine squared alpha plus cosine squared beta plus cosine squared gamma, you just get 1. Okay, so that gives you a relationship between the three angles, the three direction angles. So in reality, you only need to find two of them. If you find alpha and beta, then you can solve for gamma, right, just by doing this. And then taking the square root, and then taking the arc cosine, right? So that just gives you the relationship between the three direction cosines. Quick example, maybe. Okay, so here's a vector. It has components 5, negative 14, and 2, and we want to find the three direction angles. Okay, so what do we need? Well, right, so we need the components, and then we need the magnitude. So we have the components, we just need to find the magnitude of u. So the magnitude of u is just the square root of 5 squared plus negative 14 squared plus 2 squared, which I think you get the square root of 225. I'll just double check that. Yep, 225. And the square root of 225, well, that works out nice. It's exactly 15. Okay, so don't count on that always happening where you get, right, where the denominator turns out to be a perfect square, right? It just happens to be the case here. Okay, so the cosine of alpha will just be u1 over the magnitude of u. u1, of course, is just 5, and the magnitude of u is 15, so that reduces to 1/3. So alpha is just the inverse cosine of 1/3. And I didn't say how far to round, but again, we'll work in degrees, and let's suppose we want the nearest hundredth of a degree. So this is about 70.53 degrees. Okay. So you get the idea. Cosine of beta will just be u2 divided by the magnitude of U. So here the numerator is negative 14, the denominator is 15. So beta then will just be the arc cosine of negative 14 over 15. And that's approximately 158.96. Yep. Remember, these angles can be bigger than 90 degrees, right? And it is in this case. It should not be bigger than 180 degrees, right? So if you remember, the range of the arc cosine function goes from 0 degrees to 180 degrees, or from 0 to pi. So it works out perfectly, right? And yeah, if you ever get an angle that's bigger than 180 degrees, you're probably doing something wrong. Like, let's say you want the angle between these two vectors here. So when we're talking about the angle between these two vectors, we don't mean this angle, right? We mean this angle, the smaller of the two, right? Which would just be 360 degrees minus the previous angle. So, yep, when you talk about the angle between two vectors, it should always be between 0 and 180 degrees, or 0 and pi radians. Okay, so just to finish the example, the cosine of gamma will be u3 over the magnitude of u. So u3 was 2, so 2 over 15. And then the inverse cosine of that, sorry, it's 2. 82.34 degrees. And that's it. So, right, those are the direction cosines. I hope that example helps a little bit. Okay, so the next topic we want to discuss is the idea of a projection. So we're given two vectors, let's say u and v, and again, here are the arrows, right? And we want to project the vector u onto the vector v. Okay, so what does that mean, right? So the vector v is in this direction here, so I'm just going to kind of draw the line that the vector points in the direction of, right? And the idea is to take the vector u and project it. So that means we just want to go straight down. Well, it's not exactly straight, but let's try that again. Straight down until we hit this line. Okay, so at the point we hit the line, we're going to say that that's the endpoint, or the terminal point of a vector starting at the same origin as vector u and v, and just drawing a vector till we hit that point. Okay. So this vector here, this will be the projection of the vector u onto the vector v. Okay. For those of you who've taken physics or engineering, I think this is a pretty familiar situation here. Right? So let's suppose you just have a ramp and you want to push a box or a crate up the ramp. Or let's say we want to pull it, right? So we attach a rope to the box and we pull it in this direction here. So this is the force we apply to the box, right? So what actually happens? Well, if the force is strong enough, we can drag the box upward along the ramp in this direction. But what happens is only the force in that direction matters, right? So we have the force in this direction, right? That's the force along the ramp. But then, because of the direction of the force, we're actually pulling it up just a little bit. So there's also a component to the force that's perpendicular to the ramp. Another word for perpendicular is normal. So this is sometimes called the normal force. And in this case, the red vector here, well, that's the force that's parallel to the ramp. We can call that the tangential force. It's a little sloppy, but yeah, so tangential. Right, or parallel to the ramp. Okay, so that's what this projection of u onto v is. It's sort of the amount of u that's contained in v, right? The amount of u along the direction of v. Okay. So while we're at it then, of course, there will also be another vector perpendicular to that vector v, or orthogonal to the vector v, that will point this way. Right? I missed by a little bit, right? So this will not be the projection. This will be what's called the orthogonal component of u. Right, because it's orthogonal to v. It's perpendicular to v, right? Now, when I say component, notice I drew a vector, so I should say the orthogonal vector component. It's not a scalar, right? You can turn it into a scalar by just taking its magnitude. But right now we're looking for the vectors, and then if you want their magnitudes, we can find those later, right? Okay, so that's our goal. That's what we want to do. So we should give these vectors names. So for the projection vector, I'm going to call that W1. And for the vector, the orthogonal vector component of u, we'll call that W2. And these are vectors, right? Okay. So first let's look for the projection. Projection of u onto v. And we'll just abbreviate that. How about PROJ of the vector u, and then to indicate that it's in the direction of v, we'll do a little subscript v here. Okay. So first let's just get the magnitude of that vector, right? So this is just going to be W1, and we just want to find the magnitude of W1 for now. Well, that's just trigonometry, right? This is a right angle, and let's say that the angle between u and v is theta. So this is just going to be the magnitude of u times the cosine of theta. Right? So that's just trigonometry. So what we can do then is multiply the numerator by the magnitude of v. And, well, as long as I divide by that same number, I can cancel them. So why would I do that? Well, look at the numerator. Where have we seen this before? The magnitude of u times the magnitude of v times the cosine of theta. Yep, that's just the dot product, remember? But now we have to divide by the magnitude of v here. So there you go. Right, that's going to be the magnitude of the projection vector, W1. So what if we want the vector W1, right? So how do we get the vector W1 up here? Well, what direction is W1 pointing in, right? It's pointing in the same direction as V, right? So if I just multiply the magnitude of W1 times V, well, then I get a vector that points along that direction, the direction of V. The problem is that V might not be a unit vector. So if the magnitude of V is, say, 2, then you're actually doubling the magnitude that we want, right? Right. So we're not getting the same vector as with the same magnitude as W1. But that's an easy fix. I can turn this vector into a unit vector by just dividing by the magnitude of v. So now I'm just multiplying by v divided by its magnitude, so I'm multiplying by a unit vector in the direction of v. And so if we do that, now we have the magnitude of W1, which was U dot V, right, times V itself, divided by the magnitude of V. And of course, this is also divided by the magnitude of V. So we get U dot V divided by the magnitude of V, or the norm of V, squared, all times the vector V. Okay. So I hope that's clear. And so that's the answer here. This is going to be U dot V, and again, that's a number, divided by the magnitude of V squared. That's also a number. And to make it a vector, you just multiply by V. Okay. So what's in the parentheses here is simply the scalar multiple, right? This is just C times V, where C is the scalar multiple that you need to multiply by V to get W1. So in this picture here, it could be maybe 2.5, maybe a little bit less, because this would be 2 times V, this would be 3 times V, so yeah, this might be somewhere around 2.5 times V. So in this case, the C here would be about 2.5, give or take. Okay. So yes, the thing that's in the parentheses here is just some number that you have to multiply by V to get W1. But that's it, right? So that's the formula for the projection of U onto V. Right. Now, what about W2? So how do we find that vector? Okay, so there's a couple ways of going about it. The hard way is to say, well, let's see, can we find this angle here? Well, sure, it's just going to be pi over 2 minus theta, and then maybe play the same game. The problem is that we don't even have a vector perpendicular to V, or I should say orthogonal to V. So it turns out there's a much easier way. And so the trick is to understanding the relationship between W1, W2, and U. Right. And it's in the diagram here. It's maybe a little subtle, but I drew this little rectangle here, right? And a rectangle is just a special case of a parallelogram. So these three vectors follow the parallelogram rule. In this case, U is the diagonal, right? So that's the vector sum of W1 plus W2. So U is really just W1 plus W2. Right. Well, we already know what W1 is. That's what we just derived. This quantity right here is W1. So we're given U, we can find W1, and now we can find W2 just by subtracting, right? So W2 is really just the vector U minus W1. Okay, and if you want to write this out as a formula, right? In other words, if you don't want to calculate W1 first, well, then you can say that W2 is just the vector U minus W1, which of course is U dot V divided by the magnitude of V squared times V itself. So that's the full formula I wrote out by writing out what W1 was from up here. It's W1 is all this stuff up here, right? Anyways, oh, I didn't mean to erase that. So for those of you that have had linear algebra, you probably recognize this process. This is sort of just the very beginning of the Gram-Schmidt process to essentially find a set of orthonormal vectors. Now, we didn't normalize these, so we're not making W1 and W2 into unit vectors here. You can if you want, and that would provide you with an orthonormal basis. But in this case, we're not worried about that. We really just want the projections, and that's what this process does here. So yeah, if you've had linear algebra, you know that already. If you haven't, then you'll worry about that when you take linear algebra. And hopefully by then this process might look a little bit more familiar. So once you get used to this, the Gram-Schmidt process, even though it kind of goes on and on, is really just doing these steps over and over again. Yep, so again, that's finding projections. And again, this is a good way to understand it in terms of, say, forces and normal forces and tangential forces. So that's one application for finding projections. Okay, so we'll end with one last example here. We have two vectors, u and v, and we want to find the projection of u onto v, as well as the vector component orthogonal to v. So in other words, we want to find, right, w1 and w2 here. Right. So we're just going to use this process up here. So let's start with w1. w1, also known as the projection, right, of u onto v. It's the projection of u onto v. So the formula, I hope you remember it, u dot v divided by the magnitude of v squared times v. Right, we just did that. Oh, incidentally, of course, if you don't know the formula, don't worry about it. Obviously, you can always look these up. So when you so for your tests, I'm going to give you a whole list of formulas that you can use for the test. So basically, you'll have a formula sheet. There will be a lot of formulas in this class, and there's no reason to spend, so much time trying to memorize all these formulas like this one here. More importantly is that you know when to apply them and you know how to use them, rather than try to memorize all the formulas, right? So yeah, in Calc 1 and 2, of course, you had a lot of memorizing to do. You had to memorize all those derivatives and integrals and things like that. But in this class, there's going to be a whole bunch of formulas, and I would say even way more than there were in Calc 1 and 2. So rather than waste time memorizing any of it, just make sure that you can recognize it and know when to apply it, when to use it. All right. So with that said, we say we're given the formula, now we just have to apply it, right? So u dot v, of course, is going to be, let's see, negative 3 times 2 is negative 6. 11 times 1 is, well, 11. And then 2 times negative 2 is negative 4. And the magnitude of v, maybe we should do that down here. The magnitude of v, I hate doing the double bars here. So I'll just call it v. Or we can do the square of it, right? That's just the norm squared. It's just v1 squared plus v2 squared plus v3 squared. And in this case, that's going to be 2 squared plus 1 squared plus negative 2 squared, which of course is 9. So that's the denominator, 9, right? So we have 11 minus 10 is 1 over 9. Right. Oh, times v. I forgot the v here. Right. Yep. So w1, let's write that down. The vector w1 is just v divided by 9. So the components of that vector will be, well, 2 over 9, 1 over 9, and then negative 2 over 9. Or if you prefer, 2 over 9 times I, plus 1 over 9 times j, plus, or well, I'll say minus 2 over 9 times k. Right. So again, I'm not picky how you want to write your answer. Either way is fine. But it is a vector. I just almost forgot the v in the formula here, right? All right, well, that's w1. What about the vector component orthogonal to v? Right, that's what we're calling w2. Right. And in fact, that's the easy part, right? Because w2 is just u minus w1. So u was the vector 3, 11, 2, or sorry, negative 3, 11, 2. Now we just have to take away this vector 2/9, 1/9, negative 2/9. And so we're just going to get a lot of fractions here. See, negative 3 times 9 is negative 27, negative 29 over 9. Oh, and then 11 times 9 is 99. 99 minus 1 is 98, so 98 over 9. And then 18 minus 2 is 16 over 9. Again, don't take my word for it. I did that awfully fast in my head. But that should be the correct answer for W2. So we found W1 and W2, and that's all we needed to do in this example. So yeah, so finding projections, again, it's just making sure you know how to use this formula. Take the dot product and take the magnitude of V. In this case, the magnitude of V, of course, was 3. But in the formula, we needed V squared, which of course is 3 squared, which is 9. So don't get confused by the magnitude of V and then the square of the magnitude of V. In this case, we needed the square in the denominator. So I think that's it for this section. Maybe one more definition that might come up in the homework, and I don't know if it does because, again, it's a concept from engineering and physics. It's the concept of work, right? So naively, in your general physics course, you might remember work as force times distance. So force times distance. But that only applies if the force is in the same direction as the displacement. So if you're moving an object, say from here to over here, right? So this is my displacement, and let's make a vector out of it. Let's just call it u, I guess. So that's the vector u. But let's suppose that the force we're applying to it, right? If it's in the same direction, then of course you can apply this formula. But let's say the force is in this direction. Okay, so in this example, if this is the vector force and this is the displacement, then we need a much more general concept. In this case, the work will be the force as a vector dot product with the vector u. Right? So it's going to be the magnitude of the force times the magnitude of the displacement, which is the distance here, times the cosine of the angle between the force and the displacement. Okay. Yeah. So if theta is 0, of course, then cosine of 0 is 1, and you just get force times distance. But otherwise, right, if the direction of the force is not in the same direction as the displacement, then you want to use the dot product with the two vectors. Okay, so that should do it for this section. And again, this dot product, the main thing to remember is that the dot product is a scalar, not a vector. In the next section, we'll talk about the cross product, which will be a vector.